Okay, pre-calculus. We are heading into the world of vectors. So, introduction to vectors, and we're just going to kind of talk about them. We'll represent and operate them geometrically. So, some things we need to know about, a lot of terminology here, and then we'll have some examples, but we'll kind of try to get through it. But a scalar, we remember with scalar multiplication in matrices, you were just multiplying by a single number. So a scalar is a single number that describes a physical quantity. So sometimes it's like speed, like, 15 miles per hour, whatever. Doesn't have anything else. It just has one single attribute to it, okay? A vector, however, is a quantity that has both magnitude and direction. We'll talk about what those are, but in this case, it's like, say, like a soccer ball. That it's once it's kicked, it has a path. It goes at a certain speed. It goes in a certain direction, and so it has more than one thing going for it. And we denote a vector by this symbol right here, the V with a little bit of a kind of a half arrow on it there. What is a magnitude? Magnitude is the length of the directed line segment. And that is an absolute value thing, right? So because it doesn't matter which way you kick the soccer ball, it's going to be a positive distance. Okay, so it's the length of the directed line segment. All right, the direction. So this is the directed angle. So we have an angle between the positive x-axis and the vector. That would be your direction. Okay. All right. Some other things about them, just as we describe this variable. So as we talked about, we know if we've got this, we've got a terminal point is the tip of it, we call it terminal point or the tip, and the initial point is the tail. Okay, so the tip has the arrow up here, terminal point has the arrow, and the initial point does not have the arrow. That's the tail, so tip and tail. Think about that. Okay, and then we would denote the vector by a couple different things, right? We could just call it A, lowercase a. We could put the little vector symbol over it, or we just like a line segment, we can call it AB. But it put the little vector signal above that as well. Okay, all right. So we have a couple more things. If a vector has its initial point at the origin, so like our one down here, we're at the origin, okay, and it's in standard position. That's what it's called. It's in standard position if its initial point where it starts is at the origin. Okay, direction of the vector is the directed angle between the vector and the horizontal line that could be used to represent the positive x-axis. So in this case, here is your angle, right? 35 degrees. This is the horizontal line that could represent the x. And between the vector, that would be 35 degrees. Okay, so the direction here of A, we would say would be 35 degrees. All right, length. Length is the line segment. The length of the line segment represents and is proportional to is the magnitude of the vector. Okay, or magnitude of the vector. So if we have a scale, right, like in this case, we have a scale, and we could say that 1 centimeter equals 5 feet per second, like we did in this one. Okay, so then the magnitude of this, since we could say that, since if we measured this thing would be 2.6 centimeters. Okay, so then we would basically use this and say use our scale, since 1 centimeter is equal to 5 feet, and this vector here is 2.6 centimeters long, then I could just say 2.6 times 5 or 13 feet per second would be the magnitude of it. Okay, so let's just first talk with the examples of whether it is scalar or vector quantity. Okay, so the first one. So we're looking at, does it have a magnitude and direction? Right, that's what we're looking at. Okay, so first one, a hockey puck shot northwest at 60 miles per hour. Okay, so we have a speed, 60 miles per hour. We also have a direction. Okay, so in that case, we have a couple different things. So we know that this is a vector quantity. Okay, how about a tennis ball served at 110 miles per hour? We only have one thing here. We just have the speed. We don't have the direction of where it's going. So we don't have direction, we don't have direction and magnitude, we just have a speed. So this one would be considered scalar. Okay. And finally, the last one, If you have a sprinter that's running 100 meters north, again, we have two things. We have how far we're going. We also have a direction. So that would be a vector quantity. Okay. Remember, scalar is just a single quantity. All right. Moving on. More vector information. So we can find the direction. We can also be used as a bearing, we call it. Okay. A quadrant bearing is where we use, and sometimes we use it as the phi symbol or phi. This is a directional measurement, and it's usually between 0 and 90 degrees east or west of the north-south line. So if you think about all that stuff, that's a lot of words, right? Here's your north-south line right here. And so then your quadrant bearing is between 0 and 90 east or west. So you have their north-south line. Then we're either going to go east or west based on that. So if we're going east, like in these examples here, this angle is from that north line going east. This angle here is from the south line going east as well, okay? So, for example, this first one here, let me clear that out for a second. This angle right in here was 35 degrees, okay? We would say that that is written as, since it's vector V, we said was 35 degrees east of south, or southeast we'd call it, but east of south. So we would say south, that's the line we started from, 35 degrees, and we went 35 degrees east. So once again, we started at the south line. That's where we started. That's where the S comes from, okay, here. And then we went 35 degrees to the east. So that's how we got that idea, okay? A true bearing. True bearing is a directional measurement where the angle is measured clockwise from the north, okay? So if they don't tell us anything, then we assume it's true bearing, that we go from up here from the north. So we would look at this one and say, oh, true bearing from the north that way, okay? So that's what we would do there. With true bearings, we always write it in 3 degrees. Just something to think about. Always using 3 digits because we're assuming it comes from the north. So a direction that measures 25 degrees clockwise from the north would be written with a true bearing of 0 to 5, right? Because it's only 3 digits and it's a true bearing, we don't have to write the direction. We know it's coming from the north, and then we go 25 degrees clockwise. It always goes clockwise from the north, okay? Again, remember, if they don't give you anything, any additional directional components, it is considered a true bearing, okay? So if they give you directions like they did here, south and east, then we know it's a quadrant bearing. If they don't, then they give a true bearing. So in this case with vector V right here, this example, here's vector V. If they didn't give us any information like they did earlier with the southeast, we would say it's a true bearing from here to there would be 145. All right, moving on. Okay, so from here, you're going to need a ruler and protractor. So got to get those out, and let's make sure we work on those. I'm going to do my best to show it without having to use the protractor tool on here because I just think I'll end up screwing it up. Regardless, what you need to do is you need to use a ruler and a protractor and draw an arrow diagram for each of these. So just kind of helps us, and then include a scale. So let's just make sure that we're doing that as well. Include a scale for each of them. And I think you'd stick with inches or centimeters from here. So the first one, we go 20 feet per second at a bearing of 030. So again, looking at that, I know that this is a true bearing from the north because it's written in three digits, okay? So I'm just going to put like a north-south line, and then I'm going to put a east-west line. Now, I know because it's 30 degrees, I'm just going to kind of draw my axis as if here, just so we know. And I'm just going to label it here. This is my north, right? And then east is over here, south, and west. Okay? Now, we know that I'm going 30 degrees Okay, 30 degrees right here from the north, since it's a true bearing. It's written as 030. So if I did that, oh man, here we go. If I put a protractor in, where'd it go? Okay, awesome, I guess not. Then I would go from, remember, I'm measuring from the 30 degrees here. So this is where my zero line is going to be, is on this line. And then I'm going to go 30 degrees clockwise. So in this case, I'm going to kind of go here. This would be my zero, and I'm going 30 degrees here. I'm just kind of sketching it out the best I can. But this is the 30 degrees we're talking about. So now my new line would be from the origin here up 30 degrees, like so, okay? Okay, and that would be my vector. Now, again, I can label that. I'm just gonna label it, it's A, so I'm labeling it A right here, all right? I've got my 30 degrees. I've got my scale, I've got my measurements, my north, east, west, south. All I need now is just to say my scale. So I used, when I drew this on the paper, I used 1 inch, and I said that 1 inch is equal to 10 feet per second. Okay, so technically, since this is 20 feet, this needed to be 2 inches from here to here, right? It has to be 2 inches to get the 20 feet. Okay, so I'm basically drawing a 2-inch segment. All right, how about B? Let's go on to B. All right, so 75 pounds of force at 140 to the horizontal. So again, it's written a little differently than what we're used to seeing. So I'll just draw my axis again. So I'm going to draw one here. 140 is going to keep me above the y-axis, so I'm going to draw it a little lower as well. I can label these X and Y, all right? 75 pounds of force, 140 degrees from the horizontal. So if this is my horizontal, right? Horizontal is the X, and I go 140 degrees, it would take me to about there, right? This would be 90 at the y-axis, so 140 degrees from my horizontal. Horizontal is X, okay? Now I'm looking at drawing a 75 pounds of force. So again, if I just have a scale, let's use centimeters this time, that 1 centimeter is equal to, say, 25 pounds, okay? Well, in that case, since I'm looking at 75 pounds, my vector has to be about 3 centimeters long. So I'm going to draw a 3 centimeter vector at 140 degrees. From the horizontal, so it'd be kind of like this, and it's got to be 3 centimeters long. I mean, again, I'm just showing you on the smartboard, but you could actually measure it with the ruler, and we would have that for us, okay? Again, this would have to be 3 centimeters long there. But I have my scale, I've got the angle, got everything else labeled, and I'm good to go. Okay, let's do one more here. All right, Z is equal, and oh, I didn't label the vector. It was V, right? Because that was what we labeled it here. All right, so the last one, I've got Z is 30 miles per hour at a bearing of south 60 degrees west. So that means basically 60 degrees southwest or 60 degrees west of south, if ever want to say that, okay? So now, because I know I'm going south and west, when I draw my axis here, I'm actually going to draw them, draw it a little bit more, my x-axis a little bit more towards the top, because I know I'm going south and west, right? So when I label this, of course, north, east, west, and south, okay? So now I know, that's why I drew the axis up there, because I know I'm going to be kind of dealing with this area down here, because I'm going south and west, okay? So as I do that, So 60 degrees west of south. So what that tells me is I'm taking it from the south line, right? The south, and I'm going 60 degrees from the south line to the west. So when I use my protractor, this is going to be my 0 here, and I'm swinging it 60 degrees this way. Okay, 60 degrees that way. Because I'm starting at the south line, I'm going 60 degrees to the west. All right, and then my vector can be here through that. Okay, now if I drew this, again, I have to go according to my scale. So if my scale says that I am, say, go back to inches, 1 inch equals, and I'm going to show you just a different way. 1 inch is 20 miles per hour. Well, since it's 30, this segment here would have to be 1.5 inches, right? So this vector I would try to draw as 1.5 inches long. Okay, I know it's not to scale because I'm on the smart board doing the best I can with that. Okay, so I have everything there, just got to label it vector C. Okay, I've got my scale, I've got my graphs labeled, I've got my vector, I've got my angles. And that, again, remember, is 60 degrees west of the south line. So I started at the south line here, and I went 60 degrees to the west. All right. Let's keep rolling. All right. So when we have these vectors, we'll have to look at some different types. Parallel vectors, okay? Obviously, you can be familiar with those. They have the same or opposite. Parallel vectors, they have the same or the opposite direction, not necessarily the same magnitude, okay? They're not going to cross. You're very familiar with parallel. Equivalent vectors, they have the same magnitude and direction. Equivalent vectors, same magnitude and direction. So A equals C because they have the same magnitude and direction. They're equal. Notice that A is not equal to B. Even though they're parallel vectors, they're not equal to B because this distance here is longer than this distance here, okay? And same thing, A is not equal to D because A goes in this direction, D goes in this direction. So to be equivalent, they have to be the same magnitude and the direction. And then you've got opposite vectors. The opposite ones would be, they have the same magnitude, but they go in the opposite direction. We will write that as opposite would be of A would be negative A. So in this case, E is a opposite vector of A. If you look at E, they're parallel, but this one's going the opposite way, right? This one's going in this direction, while A is going in this direction, but they're the same magnitude, same direction, okay? Or same magnitude, opposite direction. All right, so when two or more are added, we call those the resultant. All right, so the resultant vector has the same effects as applying one vector after the other. So geometrically, we can use that by two different methods. We've got the triangle method and the parallelogram method. Basically, you're going to draw them, and then you're going to add them up. Okay, triangle method. We call this also tip to tail. So you're going to basically translate these vectors so that the tail of B touches the tip of A. So I just kind of move this thing down so that the arrow part, we go boop, boop, okay? The tail of B touches the tip of A. Then I draw the line that connects both of them to form a triangle, and that becomes my A plus B, all right? In the parallelogram method, okay, a little bit differently, instead of going tip to tail, I'm going tail to tail. So they're initial points, not the points with the arrows. So I translate them so that they look like this with their tails touching, and then I'm just going to draw a parallelogram using the opposite sides, right? So I'm going to draw in these here to make a parallelogram, and the one that splits them, the diagonal that splits them into two congruent triangles is your A plus B, okay? Different forms, they work differently for each other. So just thinking about this, when you use the parallelogram method, it's got to be repeated in order to find the resultant of more than two vectors. So you got to do that multiple times. You're finding more than two. So the triangle method is easier when you're trying to find the resultant of three or more. If you're finding two, it's the resultant of two. It's pick your poison. Either one works. But if you're using three or more, it's easier to use triangle. Just continue to place the initial point at the terminal point of the previous vector. So you just kind of keep putting them tip to tail, and then you're in good shape. All right, so let's do a couple examples of that, and then we'll be done. Whew, that's a long one. All right, so in this one, in this competition, Tia walks north 50 degrees for 120 feet, and then walks 80 feet due east. So you got these vectors here that denote that she went 50 degrees this way, and then went 0 degrees basically, or straight over due east 1.6 centimeters. So draw a diagram to represent P and Q using a scale of 1 centimeter equals 50 feet. Okay. So we're going to need a ruler and protractor again. And now I basically want to draw a couple lines. So I know, since my diagram here, I know it's got to be 2.4 feet. Okay, I've done that. And I know that this one has to be 1.6 centimeters. That's already been done. All right. So I really just want to look at using the triangle method. I'm going to use both here. So first thing I'm going to do is I'm just going to put a little coordinate axis system on here, or just a vertical line, because I can go from there. Right. So now if I draw my vector, and again, I'm using a protractor, so I'm just going to do my best to do this. But if I put this from, say, here, remember what I'm drawing is I want it to be at 66 degrees, okay? Because that's what it tells me. It says that I went to sorry, not 66 degrees. I got ahead of myself. So I want to go 50 degrees from the north line, right? It says 50 degrees east of north. So here's my north right here. So I want to go 50 degrees this way, okay, and make that vector. Okay, that's got to be 2.4 centimeters. I'm just kind of copying that one there. So that's 2.4 centimeters here. Okay, now tip to tail. So I'm going to take from this vector right here, this 1.6, and I'm going to draw that straight across at 1.6. We're just going to have to bear with me with the measurements, but so 1.6 centimeters here. And then what I do is I draw the vector that connects those. Would be here to form the triangle, and this would be, if this is vector P and this is vector Q, then this is P plus Q, okay? So then I can measure that, and I measure it, it should be 3.7 centimeters just by measuring this line right here, this vector, okay? Now, remember I have my scale, so my scale is 1 centimeter is 50 feet, so I go 3.7 by 50 feet equals 185 feet, okay? And what direction did we go? And what was the degrees? Again, I can measure now with my protractor and say, well, this from north going east, my protractor says it was 66 degrees. So I went 185 feet and I went 66 degrees east of north. That would be my answer to this question. How far? 185 feet. And what quadrant bearing is T from her starting position? Well, she went 185 feet and she went 66 degrees north or east of north. Okay. Now you can do the same thing with the parallelogram method. So I'm just going to show that really quick. So if I do the same things, I'll use red again for that same vector. Okay, so if I go and draw, this is, say, the P vector. Ah. Come on. I'll do it down here. Okay, cool. All right, so let's say I did, so I got this here. I'm just gonna try to do the same thing and use my P vector here. Let's use my Q vector going this way, okay? So I can label those. This is P, this is Q. Now to do the parallelogram, I'm going to do another one of these. Because now I'm going, with this one is a little bit different. Oh, I'm sorry. This one actually has to come down here. Yep, Q would come down there because I'm doing the parallelogram is tail to tail. So now I do that. Now I need to draw, I'm just going to sketch it just to show you that it's the line here and then the line here to complete the parallelogram. And then this distance here, right here, sorry, that's terrible. This distance here becomes your P plus Q, okay? Still going to be the same stuff, same measurements. If I take it from north, it's still going to be 66 degrees. And if I measure that, it's still going to be 3.7 centimeters. So I'll still get the same answer there, okay? All right, let's do one more example here and call it good. So this one, we don't have the diagrams to work with. So now I'm just going to go ahead. I'm going to start by drawing an axis system. I've got north. I'm going to label those north, east, west, and south. Okay, so it tells me that Shelley walked 2 kilometers north, 30 west, which means 30 degrees northwest, 30 degrees west of north. Okay, so that's where she first walked. And so I'm going to draw that one like this. So remember, I'm going 30 degrees from the northwest. So that'd be 30 degrees. So when I draw that vector, it's going to go through here. And I've got to have a scale. So let's just keep it simple here and say that 1 centimeter equals 1 kilometer. So this thing should be 2 centimeters long. Okay. Then she went 2 kilometers directly east. So from there, she went 2 directly to the east. Again, that should be 2 centimeters this way. So what does that put us? So now I can kind of measure that stuff, right? So now I'm looking at this new vector from, because this is the starting spot, right? This is our camp, is the origin right here. So how far is she now from the camp? It would be this part right here. So if I measure that from north, right? So if I take this from the north, I use my protractor. Okay, that's 30 degrees. What's the distance? I use my ruler. 2 centimeters. So 1 centimeter is 1 kilometer. So we know that she's 2 kilometers, but her measurement now is 30 degrees east of north. Whew. Okay, a lot to that one. Rewatch if you need to, but we'll bring our questions. Talk to you next time.